Hello everyone. Today we'll be discussing a few visualizations which can be used to represent your data. And many a times these representations can give us better insight into our data. Okay. Now first of all let me start with a story about why visualizations are essential. How much role can they play? See, there are people who feel that pictures are for dumb minds, and if I understand numbers then I don't need pictures, etc. But that is not really the case. Many a times pictures can help you a lot. Okay, so this is some hand pump which actually supposedly changed the course of epidemiology. Of course this is a replica because this is quite an old pump. It won't be in such a good shape now. Can you find something peculiar or strange about this pump? So, this is supposed to be a hand pump, but this handle is missing. Okay, there is no handle here, and the that is actually an interesting story. So, this pump is from UK. So, in the 19th century, there was worldwide cholera pandemic, and Soho district of the city of Westminster in London also had a cholera outbreak in 1854. It is known as 1854 Broad Street cholera outbreak. This outbreak killed 616 people, and it is best known for the physician John Snow's study of its causes and his hypothesis that germ contaminated water was actually the source of cholera rather than particles in air. In those days, the source of cholera was unknown, and many people used to think that it transmits through air. But John Snow's study established water pathogen in water as the source of cholera, and this discovery came to influence the public health and construction of improved sanitation facilities beginning in the mid 19th century. So, what did John Snow actually do? So, there are two aspects of his work. First is visualization of the available data, and secondly, his was probably the first double blind experiment in the history. We have seen a bit about uh, blinding and design of experiment in one of the earlier lectures. So here also what he did was, let me first talk about that and then I'll come to the visualization part. Okay, so there were two major companies which were providing water to households in Soho, and both these companies used to source water from Thames River. Okay, and what Jon Snow did was he collected data from people about how many patients they had in their home, and which in a home there could be multiple taps, so generally water from which tap is used for drinking, etc. And it was blind study in the sense that the participants did not know that which company is providing them water is a cause of this factor, cause of cholera, and of course the providers also didn't know anything. It was just recorded that okay, these taps are corresponding to people who have had corresponding to families who have had many patients, and these taps are corresponding to families who have had less patients. And then later he found out that out of these two companies, one company was sourcing contaminated water from Thames, and other company was having its machinery at an upriver location where the water was of better quality, and there were very few patients in homes which got water provided by this company who had an upriver source of water. Okay, and now comes the interesting visualization part of the data. See, this is a colorful version of John Snow's graph. Of course, in his days it was a hand drawn black and white graph. This is a colorful version. What does this graph say? This graph actually gives us, let me, yeah, you can see a tap here, then you can see a tap here. So these taps are actually locations of the hand pumps. Okay, and the red bubbles represent the cases. So a bigger bubble means large number of cases in that area, a small bubble means very few cases in that area, and so on. And now you can see that majority of the cases are around this tap. Around this tap there are almost no cases. Similarly, around this tap also very few cases. Around this tap again no cases. So majority of the cases are around this tap. So John Snow realized that probably this hand pump is providing contaminated water, and that is causing a lot of people to get cholera. Now, of course, telling people not to use this water was not going to work because, as I said, many people did not believe, in fact, they did not know that water can cause cholera. They thought that it was caused through air. So, what John Pump did was he simply urged authorities to remove the handle of that pump. And if the handle is removed, then of course you cannot access water, you cannot draw water, and the pump became unusable. And as a result, later it actually led to reduction in the number of cases. So a simple graph can actually give you a clue to such causes. Okay, and now coming to the part where why do you need pictures in spite of having numbers. Okay, so here is one example. Suppose we have collected data on two quantities. Let me denote them by x and y. Mean of first quantity is 54.26, average of second quantity is this, and standard deviations are given here and correlation is given here. So you know all the numbers that you need to know. But from this, can you figure out how the graph of these two quantities would look like? We are going to learn this particular graph called as scatter plot. So how this scatter plot would look like? Can you figure out from this? Now let me show you some pictures. See, all these graphs are corresponding to the same set of numbers that I presented on earlier slide. So in all these graphs, x mean is same as that value, y mean is same as that value, and so on. You can see a dinosaur, one ellipse, two ellipses, star, 5 parallel lines, 4 vertical lines, a cross, 2 parallel lines, 2 vertical lines, and this strange arrangements, slanting lines, everything. So even this dinosaur could be constructed from there. Okay, so what does it mean? That just knowing this is not enough. We need to see the spread of data, because see, correlation seems too low. Still you could draw a dinosaur from there. So if your data is actually spread like a dinosaur, it means that even though correlation is low, if you know x point, you could guess y point with quite certainty, even though correlation is low. Okay, hence we need to see pictures even though we have numbers. So never ignore the visualization component of your data analysis. Okay, now let us study some graphs one by one. This is the data on highest driving speed in miles per hour till today. So there are So this is a data on highest driving speed in miles per hour till today. These are readings from US, not from India. So that's why you can see very high speeds. So this is data collected from women, and then we have data collected from men also. Okay. Now we can see here that in men probably the 3-digit numbers are occurring more frequently, whereas in women 2-digit numbers are occurring more frequently. But if I want to confirm my hypothesis, then I can take help of some pictures first. Of course we'll need to make it more formal, etc., comes later. The simplest graph that we can draw is known as dot plot or individual value plot. So what is a dot plot or an individual value plot? So what we do is, corresponding to every value we draw a dot. So for example, we have some woman who has driven at 80, so we have a dot at 80. Okay, and if there are many occurrences of a particular value, we draw multiple dots, one on top of each other. So the number of dots represents frequency. Okay, and now in this dot plot you can see that for males the distribution is slightly towards right compared to females. Okay, in fact if we draw this vertical line around at say 120, then we can see that there is only one female who has driven at a speed beyond that, but there are many males who have driven at speeds beyond 120. Okay, plus even the peak, okay, the highest number of occurrences for males, it is near 112, okay, somewhere here, whereas for females it is somewhere near 85 or 80. Okay, so this means that even a simple dot plot can tell me a lot about spread of my data. Another example is bar plot. This bar plot is useful when I have categories of some variable and then some similar type of readings on those categories. For example, here we have many countries and then we have water consumption, per capita water consumption for those countries, per capita per day. Okay, so this data is actually real data taken from this paper. So for Spain you can see water consumption in liter is beyond 250, for Norway it is somewhere around 230, and so on. And the interesting aspect of this graph right now is that the bars are arranged in the decreasing order of their length. So Spain is the topmost spender when it comes to water consumption, and Lithuania is the one with the lowest consumption, and they are arranged in the decreasing order. But in general, in a bar plot, it is not necessary to arrange the bars in the decreasing order. You could choose to make them decreasing, increasing, or you could arrange them alphabetically as per categories. Anything is fine. Plus, as of now, this is a horizontal bar plot. You could draw a vertical bar plot where on x-axis you will have these countries, and the bars will be tall instead of horizontal. Okay, so this is bar plot. Sometimes what we measure, the variable that we measure may be continuous and we may not have many categories. For example, we asked many people, how long did you sleep last night? Okay, for how long did you sleep last night? Now when you ask this question, some people might say I slept for 4 hours 20 minutes. Some people might say I slept for 6.5 hours. So we can have fractional answers, right? So we are going to study later such types of variables are called as continuous variables. So for representing such data, we can draw what is known as histogram. So what do we do here? We have hours of sleep on x-axis, and on y-axis we have count of people. So what does this number 1 mean? It means that in our sample there was one person who reported sleeping in 1.5 to 2.5 hours, somewhere between 1.5 to 2.5 hours. Then there was one person who reported sleeping for 2.5 to 3 hours, somewhere between this. So majority of the people slept somewhere around 6.5 to 7.5 hours, right? 45 people slept, and this height is height of the bar represents the count. So up to 45 we have drawn this bar. So majority of the people slept for this duration. Then the next contender was 7.5 to 8.5, next was 5.5 to 6.5, and so on. Okay, one interesting point about this graph is that this graph is fairly symmetric. What do I mean by symmetric? We can see that there is a peak in the middle, and on both the sides the heights of the bars goes on decreasing in a roughly similar fashion. So this is typical for what is known as a normal distribution in statistics. Okay, so this bell shaped curve is called as normal curve. We are going to study in detail the theory of normal curve, but this approximates this histogram quite well. Okay, of course at some positions there may be slight error, but as we increase data size it may be more or less matching. So this is a symmetric graph because there is a peak in the middle, and on both the sides they have almost same distribution. So if I fold the graph in the middle, it is more or less overlapping each other. However, not every data would be symmetric. Here is another data set. So people were asked, for how long did you use computer last week? Now you can see that majority of the people have given answers in the lower range of the data, so less than 15 hours. However, there are people who have used computer for more than 80 hours. Okay, so here the peak of that curve is towards left, and we have a long drawn tail towards right. Such graph is known as positively skewed graph. Okay, this is known as positively skewed graph. We will see in detail again positively skewed, negatively skewed. Negatively skewed would be opposite of this. Now, why this data is showing this particular pattern? See, sleeping, there is not much heterogeneity. More or less all adults need similar amount of sleep, whereas computer use is a different variable. There are people for whom computer is absolutely needed for their profession, and even for pastime they use computer, so they'll be here having showing very high computer usage. But then there are many people who may not really need computer much in their daily lives, so they'll be here where the computer usage is very less. Okay, so when we have such variable, when there is lot of variability in the values, many a times this type of graph could be observed. And now if I try to fit or overlay a normal curve on this graph, it looks ridiculous. For example, normal curve says that there should be some people here, but there is no one here. Okay, it's a negative area. Similarly, normal curve doesn't expect this person to be here. Sorry, this person to be here. Then this is exceptionally tall. The curve predicts the height to be somewhere here, but this is exceptionally tall. Okay, so for such data sets, we may need to use some other distributions. Now, another important graph is box plot. So what is a box plot? So here is an interesting example. Suppose we ask students what is their GPA, grade point average. Again, this data is from US, so the scale is 0 to 4. You know, generally people tend to say that backbenchers are bad at studies, front benchers are more serious. So someone wanted to see whether that is really true. So he categorized students in a class into two categories. So by their typical seat location, front benchers, middle benchers, and back benchers. Now, and then collected data on their grade point averages, and he drew box plots. Now what do these box plots indicate? First of all, how is it drawn? This purple line in the around the middle of the box is known as median. Okay, what is median? Median is that observation which divides the data into two equal parts. So 50% of the data points are below this line, 50% of the data points are above this line. Now we can see for front benchers the median score is higher compared to middle and back, but for middle and back benchers it is almost the same. Okay, then the lower boundary of this box is Q1. What is Q1? Q1 is first quartile of the data. What do I mean by first quartile? Only 25% of the observations are below this boundary, whereas remaining 75% are above this particular line. Similarly here, only 25% are below this boundary, 75% are above this lower boundary. Okay, so this is Q1, and upper boundary is known as Q3. So what is Q3? Q3 is kind of opposite to Q1. So above Q3 only 25% observations are there, and below Q3 75% observations are there. So height of the box kind of represents spread in the data, and we also have these additional lines emerging out of these box. They are known as whiskers. Okay, so sometimes this is also called as box and whiskers plot, and the length of these whiskers also tell us something about spread of the data. So if the length is more in this direction, then it means that the spread is more in this direction. And unexceptionally large or small values are denoted by stars, and they are called as outliers. So these are values which are unexceptionally small. Similarly here. Okay, and now you can see that these two boxes are more or less at similar heights, and their heights are also same. So it means that middle and back benchers probably have more or less similar distribution of their GPAs. Front benchers tend to have slightly higher GPAs, but in middle and back there is not much difference. Okay. Another important thing that we can decipher from a box plot is symmetry of the data. So we saw symmetry and skewness earlier in the histogram. So if the data set is symmetric, then this purple line, the median, is almost roughly at the middle of this box. Whereas if this line is towards one side, maybe towards bottom or towards top, then we say that the data is skewed. Okay. If this line is towards the lower boundary of the box, then we will say that the data set is positively skewed. If the median is towards the upper boundary of the box, then we will say the data is negatively skewed. Okay. So positively skewed, negatively skewed, and if the line is almost at the middle of the box, then we will say that the data set is symmetric. Is it okay? So this is another graph called as box plot, which can be used to represent such data sets. Another interesting graph which many of you might have seen a lot is pie chart. Generally, when budget is declared, newspapers print how rupee comes and how rupee goes, what percentage of spending is there for every sector, what percentage of earning is there from every sector, etc. Okay, so pie chart is a very popular graph, but it can also give us very interesting insight. So this is data from 1950 Winder and Graham study. So this was time when smoking was considered as cool. People did not know that smoking can cause lung cancer. Some doctors had started suspecting that, but they didn't have enough evidence, and hence they started collecting data. So this data set contains representation of division of entire population into two parts: smokers, heavy smokers, and light or non-smokers. And you can see that 74% are heavy smokers. As I said, in those days smoking was considered cool, so smoking was more common, and 26% are light or non-smokers. Now let us see another graph. This is a graph of lung cancer patients. Now in lung cancer patients, the distribution has changed. In lung cancer patients, 96% of the patients are heavy smokers, and only 4% of the patients are coming from light or non-smoker group. Now, ideally, if there is no relationship between smoking and lung cancer, then proportion of smokers in entire population should remain more or less same as proportion of smokers in lung cancer patients, if there is no connection between smoking and lung cancer. But we can see here that when we are talking of entire population, proportion of smokers is 74%. However, if I focus on lung cancer patients, then almost everyone is coming from a smoker group, heavy smoking group. 96% of the people are from heavy smokers group, which means that smoking and cancer are somehow related. And when I say somehow, they are positively related, means smoking is associated with higher occurrence of lung cancer. Higher smoking is associated with higher occurrence of lung cancer. So this is a very beautiful example of how a very simple graph like a pie chart can lead to interesting insights. Okay, now so far we have considered, for example, here I have considered two categories: smoking, yes, no, and lung cancer, yes, no. Then here we had one variable GPA and categories as front bencher, middle bencher, back benchers. Here also we had only one variable, computer use. What if I have two variables in which and both of them are measured on a what we call as continuous scale? I'll define it later. And we want to see relationship between them. So this is one example. So we normally feel that person's eyesight tends to worsen as they age, as they become older, correct? So some people carried out an experiment to examine this hypothesis. So the experiment that they did was they gave some eye tests. So they basically checked how far a person can see, up to what distance a person can see. Okay, and every point here is representation of two values. X axis I have age. So for example, if I focus on this point, okay, then sorry, if I focus on this point, then age of that person is around 33, 34, something like that. Okay, and the person could see up to say 420 feet. Okay, so age is around 34 and person could see up to 420 feet. Similarly, if I go to this point, you can see my cursor moving, right? So if I go to this point, then age of the person is around 74, maybe 73, 74, and that person could see only up to 280 feet. Okay, so every point is characterized by age of that person and the distance up to which the person could see. So this kind of plot is known as scatter plot. Okay, scatter plot. So scatter plot is generally where you represent two variables, and this scatter plot is used to see relationship between two variables. So here we can see that whatever we think probably seems to be true, because as I focus on the older people, we can see that most of the points are near 300 to 400 feet, whereas in the younger generation between ages 15 to 35, most of the points are above 400 feet. So it seems that the younger people do tend to see at a very far distance compared to the older generation, and the middle aged people are somewhere in the middle. So it seems that yes, the age seems, I mean, the vision seems to be worsening with respect to age. And we will see later something called as regression. So this is a technique which can be used to capture such trends. So here this blue line is now representing the trend, because every individual have some his or her variation. Okay, so I cannot have all the points lying in this line. Why? Because it is obvious that every person who has that particular age will not have exactly same vision. Okay, so suppose I have two people, both of them with age 25, their visions need not match exactly. So these points are around the line, they are not exactly on the line, but they are more or less around the line, and this line is showing a negative slope. You remember slope intercept concepts, right? So this line is showing a negative slope, which means that as age increases, the distance up to which a person can see decreases. And this is the equation of that line, 577 minus 3 times age. So what does it mean? It means that when your age increases by 1 year, your ability to see far away, it decreases by it is expected to decrease by 3 feet. Okay, means if you could see up to 400 feet this year, Next year, you are expected to see only up to 397 feet. You may not be able to see beyond 397 feet. Further, next year, you may be able to see only up to 394 feet, and so on. Is it okay? Are you following? What all can we
Yes,
uh,
ma'am.
conclude from scatter plot? Okay. So, this is one interesting plot. And another plot is this Pareto chart. So, what is this Pareto chart? This Pareto chart, some of you might have read something called as Pareto principle, especially when you read, articles on productivity or quality control, etc. This principle comes in picture. So this data is again from some laundry performance paper. Many people were asked. So the survey was about some detergents, and people were asked, how satisfied are you with the detergent that you are currently using, and if you have issues, what are those issues, what are the reasons which make you unhappy about your detergent. So the most common reason was insufficient stain removal, and the least common reason was bad smell in the washing machine. Okay, and the other reasons are in between. I hope you can read the reasons on x axis. What is there on the y axis? You can notice that here I have one scale on left hand side, and on right hand side I have another scale on the y axis. Okay, what do they do? So on left hand side I have, oh, I thought someone entered, but okay, maybe not. Okay, so on x axis, sorry, on y axis, here I have counts. So 49 people claimed that they are unhappy because of insufficient soil or stain removal. Then 28 people claimed that they are unhappy because there are white residues on their garment. Around 22 people claimed that they are unhappy because of color fading, etc. So this part is like a bar chart. You just have counts, you have every reason, and you have counts for that reason, so you draw a bar chart. We have already seen bar chart. But here it is compulsory to arrange the bars in the descending order. Okay? It is absolutely essential that you arrange the bars in the descending order of their heights. And now this right side y axis. Right side y axis is in percentage, and the top is 100% and the bottom is 0%. So you are in the 0 to 100% range, and this red curve is actually on that scale, percent scale. So what does that curve indicate? So see the first point of this curve. See the first point of this curve. So out of whatever number of people were surveyed, 48 people said this is my reason of unhappiness. So that 48 number, if I consider the total number of people, is approximately 28% of the entire population. So this red point is at 28%. Why? To indicate that 28% people had this reason. Then the next point is around 47% or something. So this curve actually gives me what is known as cumulative percentage. Okay, we go on accumulating. So 28% people had first reason, then around 20% people had second reason. So total number of people, total proportion of people who are unhappy is around 48%. So this point is around 48%. Then if we add the third reason, then that gets increased to 60%, and so on. Okay, so this gives me cumulative increase in the percentage, okay, or proportion. Okay, so because we have arranged the bars in the decreasing order, okay, because we have arranged the bars in the decreasing order, this is the topmost or the most important reason. Why do people draw this Pareto chart? See, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 different reasons which are making people unhappy. But not all these reasons are equally important. And Pareto chart tells us importance of each reason. So Pareto chart tells me that if I remove these first two problems, if I somehow fix my detergent to remove the first two problems, then I'm automatically making 50% of the people happy. Okay, even though there are 8 reasons, other reasons are comparatively minor. So with just these two, I'm automatically making 50% people happy. In fact, even with just one reason, I'm making more than 25% people happy. Okay, so Pareto chart is useful for assessing such relative importance of various factors or various reason. As I said, Pareto principle is sometimes also called as 80-20 rule. Like many a times, 80% of our time is spent on 20% of the task, and that's uh, harmful for our productivity, etc. So people keep on telling. Okay, so Pareto chart is a chart which can help us locate the most important causes of something, or the most important factors contributing to something, etc. Is it okay?